Just exactly what is gravity gradiometry? What are its advantages? How is it being successfully used in exploration today?
In some of our European surveys, we've identified structural changes at depth where it was unexpected by the operator.
Now, the added benefit of working with the FTG in this migration workflow is that we're modeling for depth. So we do get a sense of depth sensitivity in this exercise.
It's an exciting time to be over in North America. Obviously, we like being in other parts of the world, but it's good to see the planes come over here. And I know we've acquired a lot of data in Canada over the years, and so this is another great opportunity.
Hi, and thank you for joining this podcast by Bell Geospace. My name is Brian Main, and I'm very excited to join Bell as Business Development Manager for North America, mainly because they've got two systems flying in Canada right now. And I would say more importantly is that they've made some very significant recent developments and improvements in processing and interpretation of their data. We're going to discuss that briefly today, and I say briefly because we plan on releasing a more elaborate, extensive webinar, which will include more technical details and hopefully an exciting case study. We also don't want to take too much of your time today. So I'm joined by Bell Geospace's Colm Murphy, who is Chief Scientist, Richard Furnell, who is Senior Geologist, and Joel Purrier, who is Global Operations Manager. Now, I've spent, I'd say, a great majority of my career devoted to improving gravity data that can be delivered from an airborne platform. And when I say improving, I mean kind of the signal to the noise ratio that's delivered in post-process delivered data and data that can be acquired from an airborne platform, meaning you could acquire a lot of data very quickly. I am absolutely convinced that this type of data can make a material impact in mapping subsurface geology and in exploration for commodities of interest today, such as uranium, gold, copper, critical minerals, and other applications such as geothermal and petroleum. Now, due to the popularity of gravity gradiometry in the rest of the world, Bell Geospace has been flying their full tensor gravity gradiometer, that's FTG, in places such as Malaysia, Indonesia, Africa, and Europe. And it's only recently that some systems have come back to Canada, and we're going to, or I'll discuss this with Joel later on in the program. But for now, I thought we'd start with Richard. If you could possibly describe to the audience who may not be familiar with gravity gradiometry, just exactly what is gravity gradiometry, what are its advantages, and how is it being successfully used in exploration today? Richard?
Thanks, Brian. In a nutshell, we map subsurface structural geology. We can do this really quickly by using our aircraft. Our instrumentation is the FTG, it's full tensor gravity gradiometer, a technology that directly measures the rate of change in gravity in all directions of the field. One of the reasons why collections from a moving platform is possible. That platform is the Basler Turbo Conversion's BT-67 aircraft, which is a modified Douglas DC-3. The BT-67 is really good because it allows us good productivity, fast mobilization, and the ability to fly low and slow for acquisition, which is very important. It also is big enough to hold additional instrumentation on board, so we acquire magnetics, LiDAR, gravity, and gravity gradiometry simultaneously. Gravity is a direct function of density, and density is a physical property that's most indicative of economic deposits. By measuring the rate of change of gravity with FTG, we're able to map changes in density in subsurface geology. The gravity gradient's very sensitive to the near surface, but this does not exclude it from deeper applications such as sedimentary basins, where we've had great success in targeting known basins and new prospects for petroleum geology. The collective response is also highly suited to locating prospective geology that may host economic deposits such as metals, which is of particular interest, obviously, to mineral exploration. The impact for exploration has been immense because we've been able to map the soil density changes in the subsurface that indicate the presence of prospective geology. This has included things like the contrasts between different lithologies, especially impressive on surveys where bedding planes have been folded or tilted towards the subvertical, or simply the presence of an intrusive body. Contrasts can also be induced by structural changes, such as faults with clear downthrow, which creates a discontinuity. Lateral displacements, such as the action of shear, are also visible in the signal by discontinuities in FTG responses. We can detect multiple aspects of structural geology. In some of our European surveys, we've identified structural changes at depth where it was unexpected by the operator. FTG provided new information to exploration teams, and that allowed them to reevaluate their acreage and identify new targets. It's a great technology for completing a prospect's data coverage as well, where, say, only patchy data types have been acquired, mainly perhaps over mine areas, for instance. FTGs allowed operators to fly between them to identify their known geology in the data, and then trace and map responses or structures across a prospect for a very limited expense. In fact, it's not unheard of for clients to actually redraw their local geological maps based on the data returned by the FTG. Some of the FTG surveys we've performed have also been known to reveal mineral alteration zones. They appear as sharpened, low density responses, and often associated with the intersection of fault structures. Additionally, deposits forming unconformities also yield a negative response. Often a negative FTG response is visible with a positive magnetic response, for instance. A big advantage of FTG is that it can help to see beneath overburden. It's not blocked by that, and it's quite complementary with other data such as electromagnetics and seismics. For instance, the FTG data can be used to focus EM surveys, or where EM surveys have already been collected, it can help prioritize and improve interpretation of anomalies for follow-up. For seismic, it helps improve impedance issues caused by velocity ambiguities. Thus, it increases coherency and clarity with greater confidence. FTG is obviously also very useful when these technologies are interfered with by the geology itself. So these situations are just some where FTG plays a huge role, and our new processing techniques and workflows are also making a huge difference in pulling coherent geology out of the data.
Thanks very much, Richard. Colm, can we talk a little bit about the improvements in processing and interpretation? Because this is what really excites me. Because traditionally, there's been an issue with the challenge of signal to noise, particularly for some applications. Can you possibly explain briefly in layman's terms the latest developments and how they overcome these challenges and why it's so exciting?
Sure, Brian, and they're good points for us all to be aware of. The greatest challenge in many ways for working with gravity gradiometry data has been capturing low frequency information for depth penetration and then capturing good stability in the higher frequency content. The low frequency challenges, it's easily addressed once you get you level the FTG signal to a tensor field calculated from conventional gravity. And what that does, it allows us to increase the value of not only FTGs offering for regional scale work, but also with increasing the value on conventional airborne gravity. What you're doing is that the impact is increased resolution for targeting deep source geology. Now, the stable high frequency challenge is when we're imaging subtle responses arising from geology in the shallow section. We've all seen maps of final processed gravity gradient data, and sometimes we get clear definition of wonderful geology where such features are shallow and they generate good density contrasts. However, there's many a time we've also seen images of data that just appear riddled with what appears to be a noise train, and this is characterized by a low amplitude, high frequency, and is very consistent and persistent across those final products. The effect has the effect of significantly rendering your data of extreme low value, especially if you're targeting subtle geology and it generates a similar signal bandwidth to the noise train itself. Traditionally, we all would have used frequency filtering technologies and various tools, but they just end up removing the key geological signal whilst you're removing the noise. So at Bell, what we've done is we've developed a method to overcome this, and we call it full tensor migration. What it does, it transforms the signal to a density field, and then it goes about iteratively modeling that to look for depth, and all the while having its input density as being a range of densities that are more geologically acceptable. The impact is absolutely amazing. It allows us to detect and map geological signal that has been previously lost. Now, I'm going to show you that in a slide here. So what you're seeing here on the left is the impact. What you have on the left is the noisy, conventionally processed gravity gradient signal. It's a TZZ response. And you can see some of the subtle linear trends through it, but they're quite weak. And really, they've been contaminated by this presence of this noise train that I've been talking about. With the migration, we can put it through that workflow, and that's what the output is shown in the middle. And you can see it's night and day. We got a lot more strong clarity, great coherency, and we're able to track nice linear faulted features. Some of those positive anomalies in the middle, they're associated with anticlinal closures at depth. Then there's subtle fault patterns cutting through them as well, which is really good. Now, the image on the right is what that chatter looks like. The migration flow workflow recognizes that I can't find geological sources in that, and so it stops, and that's what's left over. So we really are in a great means of being able to see some fantastic clear-cut examples. Now, the added benefit of working with the FTG in this migration workflow is that we're modeling for depth, so we do get a sense of depth sensitivity in this exercise, and we can see that clearly in this example. Now, this is a data set that we acquired 20 years ago, and we put it through the migration workflow last year for the Image 2023 workshop or conference. And what it is, it's the result of the migration. Now, the depth sensitivity is identified from that depth profile. That's the analysis of the signal that's at the end of the exercise. We're seeing two zones of sensitivity, around 2,000 meters depth. That's quite deep in the Bathurst mining camp area. And again, where all of the key interest is, for around 400 meters depth. Also, what we've done here is that you'll see we stopped at 400 meters because everything above that is overburden, where the signal becomes a little bit more chaotic and contaminated with that noise train. So we're imaging beneath that at 400 meters and deeper, and you can see the great clarity on that map. You can see the geological overlay. There's some fantastic agreement. That geological overlay is taken from magnetics, EM, borehole information, surface mapping, and a very well studied part of Canada. So all that is great. So the data is set up when you have this. Another more significant challenge of working with gravity gradient data is having confidence in delineating structure. There's a lot of information. So what we tend to do is reorganize the tensor, and especially the migrated output. And we call it, it's all about working the data to look for structures and lineaments. We put the data first through what we call as a contact lineament processing stream. And what that does is that it looks for a signal that's associated with buried structure and faulted lineaments. The idea is that it looks for nice long linear anomalies and extracts them, and then rebuilds the tensor accordingly. In the map that you see there is the TZZ, it's looking at density. So if we now think about the structures and the like, we can rework and revisit that with the other components. And what we're seeing in this particular one is an end result of that. The structures are identified from the horizontal components by combining the XX, XY, and YY, and they map the curvature and they're building a sense of structures. That's here in this map in the colours. The blues are localized lower density structures, and the reds are higher density structures. So we see a good variation, good mixture, and patterns and distinct linear trends are evident on them. The XZ and the YZ then are combined to map lineaments, contacts, faulted contacts, and we plot that on this map as well. So it's a real end process work, and it's full of exciting information that it means that we're using the full tensor very, very quickly to produce a geologically looking map from the geophysics. And it's set up for the geologist. And we can get a sense of that. If we zoom in on just that northern part there, and we can see in the zoomed in portion that in the central area there's some of these very subtle east-west or near east-northeast and east-west trending structures. That would be exciting because these are at 400 meters depth beneath the known areas of known mineralization. And then you can see where they're outlined or dotted there with the green X's, because there's the drill hole information. What's really good about this is that the geologist now can take this base map and start interpreting geology. And they might look for some of these key zones in the data. They see your key east-west structures, and we identify a sense of displacement on them, north-northwest orientated. And they are the two key zones for mineralization trends in the Bathurst region, and here we've got it. So all in all, this is just great news for the working geologist, because they get the FTG with these new outputs. They can then sit down and not only be confident of working with the data, but they can target their key depth intervals and start mapping prospectivity in detail beneath the overburden and so forth. So really, all in all, is that in effect, what these new technologies allow us to do is to, say, strip out the effect of overburden, focus on a key depth interval, or if necessary, go deeper and look at the basement control and the regional context. Of course, this can all be related to those challenges that are faced with exploration for uranium in the Athabasca Basin, where targeting subtle responses below a noisy overburden is quite challenging. So Brian, I hope I've answered those questions about the challenges of working with gravity gradiometry and what we at Bell are able to do now to address them. In fact, we are currently revisiting additional data sets that we have acquired across Canada, and that we're putting them through these new methods to look for some new information, and soon enough we'll have some exciting examples to show in the coming months. If these examples, of course, with their greater detail, they will be described in a webinar that we're scheduling for the fall.
That's really interesting, Colin. If I were to try to quickly summarize that, I'd say, would it be fair to say that, number one, the new processing interpretation improves the signal to noise, or helps reduce the traditional noise in the data, which enables you to see the geology clear, and also allows you, in that those depth slicing that you're talking about, allows a geologist to particular focus in if they're interested in looking at the first 500 meters or the next 500 meters or basement, they could do that. Would that be a fair statement?
That is a fair statement. And at the end of the day, yes, you can set specific depth intervals, but of course, geophysics is geophysics. Those intervals might be over 500 meters, and it might be over 2 kilometers, depending on the strength of the signature arising from the different features. But yes, you can. And you can build 2D profiles and build cross-sections from the outputs as well. You can use all of the information quite cleverly. That's
amazing. Well, I'm looking forward to seeing some of the repost results, and that we're hoping to release in the webinar coming up. So thanks very much, Colin.
Thank you.
Hi, Joel. I mentioned earlier in the podcast that the planes have been overseas and are now back in North America. Can you tell us a little bit about what they were doing and why they're back now?
Yeah. Well, the exciting news is that we've been able to acquire quite a bit of data in other parts of the world. We just finished up a over 40,000 line kilometer project in India, and now the planes are back over in North America, acquiring 2 of them actually in Nunavut in Canada.
Oh, that's awesome. And maybe for our viewers, can you tell us what aircraft we fly on and what are the advantages?
We use BT-67s, which are modified DC-3 aircraft from Basler turbo conversions. And so the benefits there is that it's a nice stable platform, large aircraft, lots of space for survey equipment, and keeps the vertical accelerations to a minimum so that we can acquire just wonderful low noise data.
Yeah, so weather is obviously a factor, but is there any other conditions that might limit time of year or whatever that might limit when we acquire FTG data?
We've acquired data in all kinds of extreme conditions, including in the fall and winter in Canada. Obviously, we start to have the most constraints as the daylight hours start to be constrained, but as far as our ability to acquire in cold weather or in fall and winter, that is definitely something that we've been traditionally able to do.
Okay, great. Is there anything else you'd like to add?
It's an exciting time to be over in North America. Obviously, we like being in other parts of the world, but it's good to see the planes come over here and be acquiring data. I know we've acquired a lot of data in Canada over the years, and so this is another great opportunity.
Awesome, Joel. For the viewers, we, as mentioned, we will be releasing a more detailed webinar in a few months' time. If you would like to sign up for notification, please click below. And we're also going to be at the Image conference in Houston at the end of August. So if you happen to be there, please drop by our booth. We'd be happy to discuss your projects with us.